Okay, let's see if we can solve this problem using Ampere's law. So we've got a solenoid, and which is just a coil of wires wrapped around, and we'll assume it's just an air-filled coil. So if the current is going up the back, it's going to be going down in the front in all of these pieces, right? So it's just a big coil of wire. And we know from before, if we do our fingers with the right-hand rule, the new right-hand rule, the field would be going around each one, and so that it's going to the right on the inside and be going to the left on the outside, right? And so if we want it, this would means that this would be the north pole of the magnet, and this would be the south pole of the electromagnet, and the field lines, would be going from the north to the south, just like a big magnet's, right, coming out of the north into the south and continuing in through the middle, something like that. All right. And so let's kind of redraw this. So first one says find a suitable Amperian path. And so remember with Gauss's law, we had to find a closed Gaussian surface, and we had to calculate Q enclosed, so forth, to get. Remember for Gauss, we're going to write Gauss. So remember Gauss was integral over a closed surface. The surface of B dot dA was Q enclosed over epsilon naught, and we found a good Gaussian surface. So this could just not B. This was E. Electric field for Gauss. This could just become EA. So if we found a surface where E was constant on the surface or 0, and anyway, had a good Gaussian surface, that way E was constant and perpendicular, and so we could make the integral just be EA, and we can do Q enclosed, and we can get E, then get an equation for E based on the geometry, knowing the direction of things. So now we're going to do Ampere, and instead of a closed surface, we're going to have a closed path. We're going to do magnetic field dot dl. So we're going to go around a path, taking dot product of B with the displacement along the path, and that's going to be equal to mu naught I enclosed. All right, so we want to make a path through the solenoid that encloses some of the current, and we want B inside the solenoid, so the path needs to go inside the solenoid so that we can calculate the B field inside the solenoid. So let's kind of take a cross section of our solenoid here and say these are the wires now that we've kind of chopped in half vertically here. And so the current on the top is going to be coming over the top, is going to be coming out. So we're going to have all these little currents. All of our I's are coming out of the page now, right, at this top piece. And so we're going to take our Amperian path to be going through the middle and then going up around the outside, going something like that. So in this diagram, it would be going like this, would be our Amperian path. Sorry. That goes around, and so this is inside, and this is outside. All right, so this is our Amperian path. Amperian, I don't know, path. Let's call it L or something. Okay. And so we're going to have some different sides, and for the Amperian path, we want to have a constant B direction, constant B on the path, or on each side of the path anyway. And then we want B dot dl, so we want B to be lined up with dl. So dl is going to be just this tiny little, if we're going around this way for our path, tiny little piece of the path, right, a little dl, and what direction is the B field in all this. So we've got our B field here, but inside the B field is going, going the other way, going to the right. So B, let's make our dl agree with our B field. So let's go around the path the other way. Go around this way for our little dl, and our B field is going this way on the inside. Right, so B and dl line up, so we're good on that side, right? B dot dl will just be B times L. B is constant on a path that's parallel to the row of coils, and so we got a constant B, so we're good on that part of the path. Here on this side, with dl going down like this, right? dl is perpendicular to B. So again, the B is going that way, right? And so in here, and so it's perpendicular to B, and so then the integral of B dot dl is 0 there, and same argument here. dl is this way, B is perpendicular to it, and so for here and for over here, the integral is 0, so we don't have to worry about it there. What about on the outside of the coil? We can take a path close. Let's take a path that's somewhat far away outside here, just not exactly just right on it. And so as we draw the field lines, I kind of ran out of room here, but looking at this side, the field lines come out of the north and go around to the south, and there really aren't very many close here. And so we'll make the approximation or the assumption that B is basically 0 right in here close by the coil. So by symmetry, it's the same on the top. So we'll say B equals 0 outside here, and so again, integral of B dot dl is equal to 0 out there as well. So our total integral of B dot dl around the whole loop would be the integral of B dot, not around the closed path, is going to be the integral, integral on the inside, right, plus going around the whole path, we're going to have plus integral of 0. Well, anyway, for the two sides, it's going to be 2 zeros, because we said the two sides are 0 because the B and the DL are perpendicular, and then the outside is also going to be 0 because B is 0. All right, so B perpendicular to DL, B perpendicular to DL, and then makes it be 0, makes the dot product be 0, and B equal to 0 also makes the dot product be 0. All right, so the whole path, the only part that contributes is this inside part, right? So our integral then, integral of B dot dl is going to be just B times L, right? B inside times the length of the path inside, or at least the length of our Amperian path inside the coil, and that's going to be equal to, by Ampere's law, where is it? It's all lost in there, mu naught I enclosed. Okay, and so if we want to calculate B inside then, which was the goal, is going to be mu naught I enclosed over L. Okay, so what is I enclosed? Well, I enclosed is the current enclosed in our loop, in our Amperian loop or Amperian path, and so we've got all these little I's that are inside of our loop, right? They're all coming out in the same direction, and how many are there? We'll just we'll just say there are n. I don't know. In this case, we'll say I enclosed is n times little I, right? If we said that we went around the whole coil, or a certain section of the coil that is L long. In our L distance of the coil, we have n turns, something like that. So then we get mu naught n I over L. So B inside the solenoid is mu naught n I over L in magnitude, right? In direction, we assumed it's going to the right for this case, the way we drew the geometry. Sometimes you'll see, this is for a solenoid, inside a solenoid. Sometimes you'll see it written as mu naught little n times I, maybe capital I, little I, it doesn't matter. Where little n is just the number of turns per length. So turns per length, turns per meter, basically, would be what it is. And so we would just take total number of turns, or say we have a solenoid that somebody wound in lab, we want to get the little n for that, we would say count 2 centimeters worth and say there were 50 turns in 2 centimeters, so it would be 25 turns per centimeter, right? And then per meter, you have to multiply that by 100, so 2,500 turns per meter. So something along those lines. So you might see it either way for B of a solenoid on the inside. They're equivalent equations. Okay, so that's that one and that one. Anyway, we're down to D. Let's see, for D. Okay, so in lab we're going to try to find the magnetic field inside a slinky. So we have the slinky is going to be our coil, and remember we have our magnetic field meters have a little circle that measures the field coming into it like this. And so if we have a solenoid that we want to measure, we can measure the field at the end, but we can't really get our thing in there perpendicular to the end. But with the slinky, we can open it up and stick our meter inside there to measure the field that would be hitting it from the perpendicular to the edge of the meter itself. Okay, so if we have our slinky like this, say it has 100 loops, and we're going to stretch it to be 0.8 meters long, 100 loops. Okay, and then we want to get a field inside of 5 milliteslas. All right, so how much current do we need to push through this guy? So we're going to connect up our DC power supply, voltage source, battery, not really battery, DC power supply, and we're going to push some current in. How much do we need to get a 5 millitesla field inside here that our meter is going to measure with this little white dot thing on the meter? Okay, so solenoid, we'll just use this first version, mu naught Ni over L. And so we want I in this case, so I is just BL over mu naught N. We wanted half a Tesla. We said our length was 0.8 meters. And we said mu naught, or we know mu naught is 4 pi 10 to the negative 7. And we said we had 100 turns in that 0.8 meters. So we can get our current. 0.5 times 0.8 divided by, in parentheses, 4e negative 7 times pi times 100. Ooh, I don't think we'll be making that much current. 3.18 kiloamps is I. Okay, our power supplies won't do that. So we won't be getting a 5, that was milliteslas. Oh, I did 5 Tesla. No, I did 0.5 Teslas, which is not 5 milliteslas. I need a couple more zeros here. So let's see. We had 3,000 amp. Oh, let's just go ahead and put it in there so I don't screw up. 0.005 times 0.8 divided by 4e negative 7 times pi times 100. Still aren't going to be able to do it. Yep, 31.8 amps. I think our supplies can do 3 amps. I'm not sure, but I'm pretty sure they can't do 31 amps. And so I'm not going to be able to get not going to be able to get 5 milliteslas out of our coils with these made up numbers anyway, which I doubt we can anyway. Okay, so that is that one. Let's go ahead and stop there.